Now that we've seen how a sampling distribution of the sample mean is constructed, let's talk about what that actually means. So we're going to describe what the distribution of the sample mean looks like when it comes from a population that is already normal. So if a random variable x is normally distributed, the sampling distribution of the sample mean, x bar, is also normally distributed. So that means if our population is normally distributed, so it's bell-shaped and symmetrical with the mean at the middle, the sampling distribution is also, well, if we could draw, is also symmetrical and bell-shaped with the mean of the sampling distribution in the middle. But remember, those two means are the same. So how does that relate? Well, we can use this to find probabilities of samples of more than one individual. So for example, if the IQX of humans is approximately normally distributed with a mean of 100 and a standard deviation of 15, we can compute the probability that a simple random sample of size n equals 10 results in a sample mean greater than 110. In other words, compute the probability that x bar, the sample mean, is greater than 110. So let's draw the picture. So here we go. So for drawing our picture, remember right in the middle is where we get the mean. And the mean is the same for both the population and the sampling distribution. So let's figure out what our standard deviation is for the sampling distribution. We know by definition that it is sigma over the square root of n. So that means that we take 15 and divide it by the square root of 10. Let's see what that is approximately. So if we get our calculator out, we are going to type 15 divide by, now the square root is right above the little x squared key on the left-hand side. So to get it, we have to hit the second key and then the x squared key, and then we'll type number 10. When we hit enter, we'll say that's approximately 4.7. We're just going to round to make our picture. Now remember, if we need to make or label, I should say, our standard deviations, we add 4.7 going to the right from the mean, and we subtract 4.7 going to the left from the mean. So if we do that, we get 104.7. The next one is 109.4, and the third one to the right is 114.1. Going the other way, we have 95.3, 90.6, and 85.9. Now we want the probability that X bar is greater than 110. So 110 is over here somewhere. And greater than means we shade to the right. So how do we calculate that probability? Well, the fact that the sampling distribution is normal helps us out. Why? Because we learned in Chapter 7 how to calculate the probability under the normal curve. So we have the same thing here. We are going to use normal CDF. Sorry, I should have written that probability notation first. We need the probability that the sample mean is greater than 110. So we're going to normal CDF. Remember, lower boundary comes first. That's the value at the left side, so 110. Since we're going greater than all the way to the right, our upper boundary is a bunch of 9s. Then we put the mean, which in this case is 100. And we put the standard deviation. Now, when we did our graph here, we rounded our standard deviation. We don't want to do that when we actually do the calculation because that results in rounding errors. So we can type 15 divided by the square root of 10 directly into the normal CDF where standard deviation goes, and it will be fine. How does that work? Well, let's go second vars to our normal CDF, number 2. Our lower is 110. Our upper is a bunch of 9s. The mean is 100. And as you can see, in the standard deviation, I typed 15 divided by square root of 10. Now, let me show you how that goes because it's slightly different than where we calculated it on the home screen. We type 15 divide. We still use the square root, but do you see how it opened a parentheses? That's fine. We typed the 10 that we need, but we have to remember to close the parentheses. And then we just go to paste and enter. And we get a probability of 0.0175. So our probability is 0.0175. So what does that probability mean? Well, we can interpret that two ways. The first way we can interpret it is just by saying the probability of obtaining a sample mean IQ greater than 110 from a population whose mean is 100 is 0.0175. The other thing we can say about this is if we take 100 samples. And these samples should be simple random samples of size n equals 10 individuals from this population and if the population mean is 100, about 2 of the samples will result in a mean IQ that is greater than 110. Now, how did we get this 2 samples? Well, that's easy. To get the 2 samples, we take the probability and multiply by the number of samples we said we took. So in this case, that is 0.0175 for the probability times we took 100 samples. And why did we choose 100 samples? We chose 100 samples because the first non-zero digit in our probability is in the hundredths place. So that's why we chose 100 samples. And if we do that, that equals 1.75. But we're talking about individuals, so we have to round. So that's approximately 2. So that's how we got 2 samples. Okay, that is it for this video. There is another practice problem here that you can try on your own, and I will go over that in the next video.